Welcome to the second part of Chapter 18 on electric charge and electric field. In this part, we're going to be exploring the atom. Now, hopefully somewhere in your academic career, you've encountered the atom. But just as a quick reminder, remember that the atom has a nucleus. In the nucleus are the positive protons and the neutral neutrons. And then somewhere associated with the atom are the negative electrons. And I know that it's common and convenient and whatever word you want here to think about the electrons orbiting the nucleus like a planet orbiting the sun. But we now know that that is not true and that the electrons are in electron clouds, and there's actually a possibility of them being inside the nucleus. Regardless of that, if we have a neutral atom, then the number of protons equals the number of electrons. And the atom is neutral because the charge of a proton has the same magnitude as the charge of an electron. And this is known as the elementary, or sometimes known as the fundamental charge. Okay, so what I'm trying to say is if we look at the magnitude of the charge of an electron, that equals the magnitude of the charge of the proton. So why am I talking about magnitudes here? I'm talking about magnitudes because I don't have to worry about the sign of the charge. The electron we know is negative, the proton is positive. I don't want to worry about that at the moment. Also, really quick, notice I'm using the letter Q. The letter Q is used to denote charge. Okay. Why is the letter Q used? Well, I don't really know. Best guess is everybody would like the letter C, but in physics, the letter C, when it's used as a variable, is 99% of the time the speed of light, which comes up when you're working with charges, and we don't want that confusion. The other thing that's going on is the unit of charge is the coulomb. So if I look at the magnitude of the charge of the electron or the magnitude of the charge of the proton, these two have the same magnitude of charge, and that's 1.6 times 10 to the minus 19 coulombs. Okay, so that C over there stands for coulombs. So now let's think about this number just a little bit. 1.6 times 10 to the minus 19 coulombs. So how many protons would be needed to achieve 1 coulomb of charge? Well, you can treat this as a unit conversion. Okay, if I take the 1 coulomb of charge and multiply by the number of protons divided by the charge of a proton, right, I get 1 coulomb times a number divided by 1.6 times 10 to the minus 19 coulombs, because that's the charge of an individual proton, which leaves me with just the number of protons. So doing that on my calculator really quick results in that I need 6.25 times 10 to the 18th protons to get 1 coulomb of charge. So 1 coulomb of charge is actually a large charge. We don't usually have 6.25 times 10 to the 18 protons floating around without electrons somewhere near them to balance them out. But to give you a little bit more perspective, let's think about this. We have 1 gram of aluminum. 1 gram of aluminum. That contains roughly 2 times 10 to the 22nd electrons. Now, remember, 6 times 10 to the 18 protons is 1 coulomb of charge. So if we look at 2 times 10 to the 22nd electrons, that's roughly negative 3,600 coulombs. This is a huge amount of charge in just 1 gram of aluminum. Or at least a huge amount of charge contained in the electrons in that 1 gram of aluminum. And imagine if it weren't 1 gram of aluminum. Imagine if it were a bigger item. Imagine it was you or I. I'm certainly a lot more than 1 gram worth of mass here, right? So why am I not automatically electrically attracted or repelled from everything? Because of the huge amount of electrons that are contained within me. And the answer is because invariably I have an almost equal number of protons. Or those two pieces of aluminum in general have equal number of protons and electrons. And because they have an equal number of protons and electrons, they are electrically neutral. Opposites attract, likes repel. Neutral objects are attracted to charged objects, but most everything in this world is neutral. Therefore, this attraction isn't always apparent or always happening. Okay, one more thing before we go here, and that is that there's a little bit more to this story. And this is not something that I'm ever going to test you on. It's not something that I'm ever going to ask you about, but it is an active field of physics research. So I wanted you to at least have a glimpse at it. So when it pops up potentially, maybe when you're reading the news sometime in the future, you can say, I remember learning just a little bit about that in my physics class. And hopefully it helps you out. And that's the fact that there's more to the story. So far we have protons, we have neutrons, and we have electrons. But it turns out, as far as we know right now in the world of physics, only one of those cannot be further subdivided, and that's the electron. So allow me to introduce you to the Standard Model. Okay, in the Standard Model, we have 3 types of particles. The ones shown in here, in purple here, are the quarks. And I love the quarks because they have fun names. Up, charm, top, down, strange, and bottom. Okay. In the green, we have leptons. And electrons come in pairs. Oh, it's not like electrons. Leptons come in pairs. So if you look, we have the electron and we have the electron neutrino. We have the muon, we have the muon neutrino, the tau and the tau neutrino. Okay. And in the blue, we have the bosons. And the bosons are charges that are responsible for regulating forces. And there's one more that needs to go in here, but I haven't found a good version of the Standard Model that brings in, I misspelled that, the Higgs boson. And the Higgs boson is really cool because it was discovered relatively recently, won a Nobel Prize. Those researchers won a Nobel Prize. And we now know that that particle is the one that is responsible for things having mass, or is related to things having mass. What you will not see on here anywhere are protons and neutrons. And the reason for that is because we can break protons and neutrons up into combinations of quarks. So if I want a proton, I take 2 up quarks and 1 down quark. And if you do a little work with the properties, you can see that that does give you a positively charged particle with all the necessary properties of a proton. But on the other hand, if I take 2 downs and an up, I get a neutron with all of its respective properties. This concludes this part of Chapter 18. In the next part, we're going to be looking at conductors and insulators.